Hi, good morning everyone. I'm happy to be here and I'm very thankful to NIT Jalandhar and Professor Urvashi Bansal for making this happen. This has been going on for almost 2 years. We started in 2023 and now it has materialized 2 years later, and I'm very happy to be here. I was in NIT Jalandhar earlier sometimes, several years ago, and had a very pleasant experience. So today, this is part of the GYAN course from the Government of India, and mainly this is about data analysis and what are the latest trend in graph analysis and scalability. So before I go into the course, I want to explain a little bit about what I think you should get out of this course, what is the focus of this course, and what is the takeaway. So the focus of this course is mainly understanding data, application data, whatever data you have in all its glory, their storage, alternatives, management, querying, generating reports. So today we are sort of drowned in the large amounts of data, and many times we don't know what to do. We want to extract useful, good information, but the trick is, how to do it properly and how to do it effectively and how to make sure what you infer is correct and useful. That's the challenge here. We will also discuss tools and techniques needed for various kinds of data analysis, right from mining, knowledge discovery, and processing of objectives. Life cycle, rather than just think about one algorithm, we want to focus on the entire life cycle. From the data, what I call sort of cradle to grave philosophy, right from the generation of data to drill down and visualization of data. We'll also do a couple of hands-on workshops or tutorials where we have developed some dashboards, and I'll show you those dashboards. So what is the takeaway for you from this course is gaining confidence in your ability to perform analysis on any kind of data. Today, data comes in very many different shapes and sizes and forms. You have transactional data, you have table-oriented data, you have CSV files, tab-oriented files, we have graphs, we have real-time data as stream data, we have images, we have video, we have all kinds of data. So the question is, how do we infer knowledge from different kinds of data, and what are the different techniques that are useful for that? Ability to choose right models and technique. This is very important. I cannot emphasize better, because when you have a piece of data, in order to do the analysis, first you have to model the data. You need to understand what model is appropriate for what kind of analysis. It is not that you can just go from raw data to inference directly, and that won't work for any large amount of data. So it's very important to understand the steps, whether you want a graph model, whether you want a relational model, whether you want some other kind of model is very important. So that is a decision you have to make depending upon what your end goal is. Confidence in your results, that you have applied principled approach for data analysis. This is very important, that you understand the data, you understand what you want, and you apply the right techniques. Why drill down and visualization is important. We'll see this when we use the dashboard. It's not enough to derive some results from the data. How do you understand it? How do you interpret it? How do you visualize it? Many times visualization of data is much more important rather than getting a lot of 100 or 5,000 numbers which are very difficult to interpret. So all of these are extremely important from a data analysis perspective. Now I also want to make sure that you ask me questions. If you have any questions, please feel free to stop me. I don't want it to be a one-sided presentation. I would like you to participate so I understand what are your doubts, what are your concerns. I'll be more than happy to answer your questions in the best way I can. So the first lecture is about understanding data and need for scalable techniques. So here we will start from the beginning. So what am I assuming? I'm assuming nothing because as the audience is mixed, I'm not making any assumptions on what you know, just to make sure that I'm not talking beyond what you know and it is not clear. I do realize that many of you are familiar with computer science and programming language, and that will only make it easier to understand, not difficult. So data collection, we just talk about data, but we don't talk about various aspects of that. Collection is one, storage is another thing, cleaning data is third thing, loading, management, and analysis has to be addressed in the context of computers. So let's take an example. You have a data set and want to discover knowledge that will be useful for your business or enterprise or community or for international relations. So this is the basic issue, right? Whoever has data, irrespective of where it comes from, whether it is biological data, whether it is social science data, whether it is data generated by sensors, the end goal is to discover something that is useful or beneficial from that, because there is a very large amount of data being generated. So your data set may be proprietary. So many of the data sets are proprietary, and people who have that are not willing to generate that. Then you have to deal with privacy issues for the data and other things. So that's a totally different thing that we want to deal with. You may have public data, but still you may have to deal with ethical issues and its usage. So for example, in law and criminal extent, you have to deal with what can be disclosed, what cannot be disclosed, what kind of aggregate analysis you can do, what is meaningful. So that is going to be very important. Then we also have what we call synthetically generated data. So what is synthetically generated data? How many of you are familiar with synthetically generated data? So what is synthetically generated data? Many times it is difficult to find real world data set for the type of analysis you want to do. So in order to overcome that, what we do is we generate data synthetically. And there are a lot of tools that have been developed to generate different kinds of data with different probability distributions or with different characteristics, with different properties. And this is very useful because you can generate much wider kind of data synthetically rather than the real world data you find. Because real world data may or may not contain all the characteristics, all the distributions, but when you want to develop your analysis tools and algorithms, you want to make sure it works across all the characteristics, across all the features. So in order to do that, we usually resort to generating synthetic data. And the other advantage is you can generate very large amount of synthetic data. Whatever size you want, you can generate, whatever configuration you want to generate, whatever properties you want. So we'll see some graph characteristics, so we can generate data with different graph characteristics. So that's very important from an analysis point of view. And of course, you have real world data. If you have real world data, then you want to use it and make sure your analysis equally applicable to real world data. So understanding the various types of data and the limitations or expectations for the data is very important. So how will you go about it? I have tried to categorize it into three categories. If the data is very small, then you can understand the data and infer things manually. This is what we were doing 30, 40 years ago. We were dealing with what we call samples. So you take a random sample of the data in order to keep it very small, and then you can analyze it by using very simple techniques, and then you try to generalize it. So if the data is very small, it's much easier to handle that. Then we have, what if the data is large? If the data is large and cannot be done manually, then you need automated techniques and algorithms to process data with a good response time. This is where all the mining, machine learning, and various other algorithms came into picture in order to deal with large amounts of data. I don't know how many of you are familiar with association rule mining. Is anybody heard of association rule mining? Association rule mining came about in the 90s to analyze what we call market basket data. So for example, your DMart generates lots of point of sales data every day. So similarly in US, Walmart generates lots of data, gigabytes of data per day. From that data, they want to know what items are bought together so that they can do the logistics for replacing the items and stocking the items. So it may depend upon the demographics, it may depend upon the region, it may depend upon various things. So there is large amount of work that has been done in what is called association rule mining. This is one of the mining that has been done, came a little bit later than clustering and classification and traditional forms of doing. So if the data is large, you need this. What if the data is very large? Then in addition to the above, you will need distributed and parallel processing techniques. So this is important to understand. This is what we call scalability. So if you have very large amount of data, you need additional techniques for processing them in parallel. In addition to doing the same algorithms, but many times converting the same algorithms into parallel algorithms is very tricky. It's not straightforward. So we'll see MapReduce. Have you heard of MapReduce? How many of you may be familiar with MapReduce? Okay, that's good. So we'll see MapReduce techniques in this course as to how we can achieve scalability using MapReduce, for example. So again, understanding the size of data and what kind of processing and resources are required is very important. Finally, you may ask, who decides what is large? That's a valid question, right? What is large? Something that is large for one person may not be large for somebody else. So it is mainly depend upon the volume and processing capabilities you have. What is your processing capability? If it takes 10 hours to analyze something, then you have very large amounts of data, you need better response time. So you need to go to scalable techniques for that. So it depends purely upon, and we also call it the quality of service constraints. So quality of service is very important, and we will not be dealing a lot with that in this course, but that is something you should understand. Finally, at the end of the day, what you need to understand is good data models, mining, statistics, machine learning algorithms. Also figure out how to leverage distributed and parallel processing. So this is really very important, even though it may look very fundamental, very simple. This is very important to understand because this determines everything else you are going to do beyond this. Any questions? So the devil is in the detail. Suppose you are given a data set and its description. We also call it metadata, and there are ways of describing the data in terms of metadata. Also, you are assumed to know the application area, which we call domain knowledge. So again, this is very important. If you are just given a data set without any information about the domain from which it comes from, it's extremely difficult to do analysis. If it comes from biological domain, social science domain, you have to have some understanding of what the domain is, what kind of things you want to infer from that domain. For example, in social science data, there is something called Big Five. They want to understand Big Five. If it is a biological domain, they want to understand something else. If it's a graph domain, you want to understand something else. So domain knowledge is also important and useful for data analysis. You cannot do data analysis in the void. You need to understand what kind of data it is. For example, if you are monitoring a bridge or if you are monitoring an infrastructure, you need to know the kind of data that is coming and what you want to monitor. So finally, your boss wants you to figure out how to leverage this data set for the business. It may be in the form of generating more customers, retaining current customers. This is very true in the mobile ISP area. You know, they keep calling you to see whether you are going to switch to a different service provider or whether you are going to be there. They want to make sure you are with them. So this is also can be done through mining and analysis. And if you are analyzing spatial data, climate change, USGS data, then it's a very different ball game altogether. Okay, so we were talking about application or analyzing data for a particular situation. Here is another one. Is there a booster shot needed for COVID? You know, this question was very relevant a few years ago, and there is something called CDC and FDC in the US, and they are charged with providing data, take input from independent advisors who will do the analysis and take a decision. So these are all experts, but they need all the information or the data to determine what to do and how to do. So again, data analysis, as I'm trying to show, that it's part of a lot of different domains in various ways. So how do you decide? The problem we have is it is possible to analyze data in multiple ways. So the question is, how do you choose? Which one will you choose and why? More importantly, once you do the analysis, you need to validate your results. I emphasize this a lot because I have students who do not fully understand the notion of validation. They think whatever the result you get is correct. And that is not the case most of the times. And how do you justify your validation? At the end of the day, you need to convince your boss that your solution is not only good and will work with high probability. So this is the bottom line. When you take up a job and you do data analysis, it is not for the purpose of academic interest. It is for the purpose of taking some marketing action. And that means a lot of money. If you make the wrong decision, spend a lot of money, no outcome, then you will be in trouble. So I call it, you know, there is this concept of doctors without borders. Similarly, I call it analysts without application boundaries, because you want to be a data analyst, but you don't want to think that I can only do analysis for one particular type of data and I cannot do for other data. You should be able to apply your analytical skills for any kind of data that you come across. Maybe you seek some help from the domain expert in understanding the data, but you should be able to do the analysis. So gone are the days when you could focus on a single topic. Today, problem solving and analysis spans multiple topics and disciplines within CS and outside CS. Hence, you cannot just focus on programming language or operating system or data management. So data analysis uses several techniques: cleaning, choosing meaningful attributes for data analysis. This is very important because many times your data contains large number of attributes. Not all of them are useful, not all of them are meaningful. Trying to analyze the entire data set is waste, and it takes more time and it's computationally more expensive. So you need to figure out which columns or which attributes are useful, which are not useful, which are dependent upon one another, so that you can reduce the number of columns. Mining machine. Hence, do not become a person with a hammer looking at everything as a nail. So if you have a hammer, you tend to think that everything is a nail, so I can hammer it. That should not be your attitude in data analysis. So instead, become a person who can match the right tool for the specific problem at hand. This requires a broader and flexible toolbox. This is very important. So think of it as a car mechanic. A car mechanic has a lot of different tools. It's not just one particular tool he uses. It depends upon what part of the car he is working on, what make of the car he is working on, what model of the car he is working on. This is also very similar to that. You cannot just apply the same technique to every data that you get. You have to determine which technique is appropriate, which technique is meaningful, and why. So, a word of caution. So many times we are in a hurry to fit a theory to the results you see. Make sure your results conform to the conjecture or proposal you have. There must be consistency between theory and experimental results. So this is what I see with my students. I see my students explaining the results even if it does not make sense. Just because they wrote a program, just because they got a result, they think it's correct. And then they try to explain the result rather than whether the result is correct with respect to the theory, whether with respect to the analysis. So there's a difference between analyzing a problem and having an idea of what you should get versus just relying upon what if your program is wrong? What if there is a mistake in your program? And that happens many times because they have not analyzed the problem and have no idea what to expect. Many programming mistakes are discovered after they are explained. Hence, this is very important. You need to have two independent ways of validation. One of them may be theoretical or analytical, the other one is experimental. These two should be done independently and they should match. You cannot just rely only on experimental results. You cannot rely only on theoretical results. Even with ChatGPT, for example, there is this problem of hallucinations. Have you heard of the problem of hallucinations? ChatGPT many times gives wrong answers. Now, if you cannot differentiate when it is wrong, when it is not wrong, you will just blindly take all the answers it gives as correct and then follow them. So that is going to be a mistake. That is also true here. That's why you need two or more independent approaches for validation. Always do sanity check. Always make sure your test data includes boundary cases, not just normal cases. These are the things that you have to be very careful about when you analyze data, because getting wrong results in certain domains is going to be extremely expensive and sometimes devastating and catastrophic. So you don't want to do those kinds of mistakes. So some clarifications, because a lot of times when I talk about data analysis, people ask me, why do I need to learn programming for doing analysis? I can do analysis, but why do I need programming? Although you may be using packages for many tasks which you do, you may have to use appropriate data structures and populate them properly with data. If you are using Python, if you are using RStudio, or if you are using scikit-learn, any of the packages that comes, then you need to understand what a table is, whether the data is input into a table format or a different kind of format, and then how to present it. So you need some understanding of data structures, you need some understanding of what kind of packages, what are their capabilities, what are their limitations in order to use it. So it's not enough just to keep using packages after packages, but need to understand the thing. So choosing appropriate algorithms for what you do is important. Figuring out plotting and visualization options, generating good understandable. So that is one question. Second question that is asked is, does the data sets used for learning matter? When we teach courses, we use one or two sample data sets, representative data sets. But when you go out, you may encounter data sets from very different domains, very different things. So the question that is asked is, I learned on these two data sets, is it good enough? That's a question. So the answer is yes and no, because understand the analysis part. Analysis part typically does not change. Data may change, but the analysis part does not change. No matter what the data is. You will be encountering different and complex data sets all the time. representativeness of the data set is very important. I have highlighted it because if the data is not representative, if the data is skewed, or if the data is biased, so there is a lot of work going on in today saying that a lot of things AI and ChatGPT are generating are based upon biased data. So just to give an example, in the US, we have different populations. We have a white population, Hispanic population, and African population. Now, if you take a data set that is predominantly white, then it is going to give results in a biased manner, or predominantly African American. So data set is very important. Or take male and female. So today in many medical data sets, there is less percentage of female data set, and that gives biased results. So it's very important to understand the data set, make sure it is representative, balanced, and there is no bias introduced due to the data set. The algorithm is the same, but the data set can introduce bias. Do not get hung up on the latest packages. Process or analysis does not change. Pre-processing is very important. How will you cover all application scenarios we are going to encounter in our career? We cannot, but importantly, we do not have to, because as I said, the process of analysis will remain the same. Details will vary, so please focus on learning the analysis, not on the data sets. Please focus on visualization and presentation. Focus on sanity check and validation. These are more important than just focusing on the data set. What about different types of pre-processing? Same as above, may have to add more tools to your pre-processing batch. At the end of the day, domain knowledge coupled with robust analysis techniques are what is important to be a successful data analyst. So this is extremely important. I cannot overemphasize this. A lot of times this is lost or missed. People are very eager to just do the analysis and not think about what they are getting out of it, whether it is correct or not. So, is the problem of data analysis new? What do you think? Obviously it is not. So, here is a slide from 1982. Nesbitt said, "We are drowning in information but starved for knowledge. This level of information is clearly impossible to handle by present means. Uncontrolled and unorganized information is no longer a resource in the information society. Instead, it becomes an impediment." We are saying the same thing after 40 plus years. Every sentence is true. We are still drowning in data. We still do not fully know how to infer knowledge, and data by itself is not enough. What is important, a lot of industries think they are sitting on gold mine, which is their data, but they don't know how to process it. So it is useless. The gold mine on which they are sitting is useless if you cannot get something meaningful out of it. So it is not enough to store, organize, and manage information, which we have done, but it is critical to extract relevant knowledge and make it available for decision making in a timely manner. So this is still, after 40 years, this is still the essence of data analysis. Then the resources were very meager, computers were not powerful, so then the amount of data they had was very large. Now we have very powerful resources, but we have 100 times, 1,000 times the data. So things have not changed very much. So let's understand a little bit about data, information, and knowledge. So this is also a pyramid that was put forth earlier in the 1980s. What it says is we have very large amount of data. We try to convert into smaller amount of information, and then still smaller amount of knowledge, and finally, if we can, into wisdom. what we call wisdom. So this is a pyramid which takes very large amounts of data and reduces it to, nuggets of knowledge or nuggets of wisdom. Now this can also be shown as the following. On the x-axis we have understanding, on the y-axis we have connectedness. So we can cast this into, we start from data and we add some relationships to data to understand it as information, and then we mine or extract patterns to make it knowledge, and then we want to extract principles to make it wisdom. Now even today, even AI, what we have, is not able to generate wisdom. Wisdom, we have from a long period of time based upon a lot of information that has been assimilated. So there are nuggets of wisdom, but can you do that with the different types of data is still an open question. So data to information to knowledge to decision and action is the process of data analysis. Casting this problem in as a data processing problem, so we have raw data, and what we want to get is knowledge, if not wisdom. And out of that we want actionable knowledge. That means you can apply this knowledge in some way to do something, to produce something, to make a marketing decision, to do some kind of a campaign, whatever it is. And in order to do that, this is the process we use. So the inverted triangle represents the reduction of data from a very large volume to small number of knowledge and wisdom and inferences. And here you can use any technique, any principle, any algorithm, and we have a large number of them. So that is what we need to focus on, how to go from raw data to knowledge, if not wisdom. And that is the whole process of data analysis. So let's look at, so what is data or raw data? You can define a raw data or base data as a value and maybe a type. So for example, if I just give you 480,000, Einstein, male, 3.14, these are pieces of data. It may be difficult to understand this data by itself because we don't know where it came from. But if I give you some more, a data by itself is difficult to understand. That's where you need, there is something called the FAIR principles. We will not go into that metadata, but let us take information. So if you add some context to this information, then it becomes much more clearer, much more meaningful. For example, 480,000 is the number of deaths in US from cigarette smoking. 3.14 is the value of pi. Einstein is a scientist. So when you add the context, this is what we also say domain knowledge or domain information, because the raw data by itself may not be meaningful in any way unless you add some context to that, which makes it easier to understand and figure out what kind of analysis is meaningful. So data science is the science which encompasses techniques, approaches, tools, abstractions of going from same thing, raw data to information to knowledge to wisdom. So not at all new, only the size, variety, complexity keeps changing or increasing. Visualization adds additional complexity. So what is the difference between knowledge and wisdom? Since we said, it's much more difficult to derive wisdom as compared to knowledge. Knowledge is knowing facts and information acquired through learning and experience, while wisdom is the ability to use that knowledge effectively, applying good judgment, insight, and understanding to make sound decisions and discern right and wrong, considering wrong. So there is a difference between knowledge and wisdom, and here is an example that is widely used. Knowing tomato is a fruit is knowledge, but not to use it in a fruit salad is the wisdom. So this is an example that is very often given to differentiate between knowledge and wisdom. Any questions or comments? So now we understand a little bit about what is analysis, why data, understanding data, and different ways in which we want to deal with data is very important. Let us understand the analysis types. So it can be classified into descriptive, and the second one is prescriptive. So descriptive means a method for quantitatively describing the main features of a collection of data. For this we use statistical and statistical measures. Descriptive analysis can be applied something like on the census data. For example, you can compute averages, you can compute frequency distributions of earnings, for example, male-female ratios, histograms of different categories. You can compute percentiles, histograms, distributions, uniform, Gaussians. So these are all descriptive analysis of data, and this is very important and very useful. Then there is the prescriptive analysis of data, which essentially means find the best course of action for a given situation. So when you are given the data, this is what we call actionable knowledge. How do you derive actionable knowledge? Not just the description of data. So the first one is more about the understanding of the data. The second one is more about deriving knowledge that can be used for some purpose. Usually this is preceded by descriptive analysis. This is process intensive, analyzes potential decisions and interactions. Sometimes you may have to do in real time. Goal is to prescribe an optimal course of action, and the techniques vary. You may use optimization, you may use simulation, you may use game theoretic approach, you may use decision analysis measures. You should be comfortable with both descriptive analysis and prescriptive analysis in order to be a good data analyst. So here are some examples to illustrate that. Suppose say we have census data. Suppose you want to know the top 5 states with largest increase in population from last census to this census. Now this falls into the descriptive analysis. You want to know, so you can look at the last census data value, this census data value, and easily compute the top 5 states with largest increase in population. You take the increase in population, sort it in some way, and take the top 5. But if you are asked to, if you want to know which state's household income is likely to rise in the next 10 years, how will you do that? You cannot do it with descriptive analysis. So this is what you need to understand. Descriptive analysis will not tell you or give you prediction. This involves prediction. So in order to do prediction, you need additional data and analysis, something like trend analysis and various other things to see them. So these two are different. So one is along the lines of descriptive analysis. The second one is more prescriptive analysis. So you need prescriptive analysis or predictive analysis. You want to explore latest census data in general, you can use both prescriptive and, but the exploration or search space may be very large. You need to have some idea of what you are looking for. Hopefully not a needle in a haystack. Sorry. Okay. So if you want to do, if you want to do data analysis, as I said earlier, you can do it in many different ways. One of them is the manual approach. So what are the pluses or the advantages of the manual approach? So you have an understanding of the problem and the context. So of course, the assumption is the data size is small. You can use intuition, match real-world semantics. You can explain your analysis or reasoning. But the problem is this can be error-prone because you are dealing with numbers and data and you are trying to do it manually, so there is fatigue, error-prone, and other things, so this can be. So just to give an example, I don't think most of you were born. NASA Mars Orbiter mishap, where British measures were used instead of US metric system, and the orbiter crashed because of the units, metric units versus British units were used, and it was not detected earlier, and some part of the mission did not go through correctly because of that. So this can happen. This is a real world example of what can go wrong if you make mistakes in the analysis. Manual approach cannot deal with large amounts of data. Complex computations are difficult or not possible. So manual is still needed in some way. We'll see why. Now, you can also use the automated approach, which is what we are discussing in this course. The positives are it avoids computation errors, assuming your program is correct. As I said, many times you want to make sure your program is correct first, or your package is doing the right thing. You can deal with very large amounts of data. You can analyze in multiple ways. Takes less time, but someone has to come up with algorithms. It is not magic, right? Someone has to develop the algorithms or the analysis. Someone has to design, program the system. Someone has to validate the system. Someone has to sanity check before using the results. So these are the things that you need to worry about in automated processing. And the third category is kind of hybrid, human in the loop. This is very much the essence of data science. Humans play a critical role, but a small role. So where do they play the small role? As a domain expert. So you can do the analysis and everything, but the interpretation of the results will involve a human who has a better domain knowledge than somebody else. So you cannot give a mechanical engineering problem to a botany expert. They won't be able to make much out of that. So you need to understand the difference between the domains that you are using. So there are some advantages to manual approach, but today with the amounts of data we cannot do that. Just to illustrate, I mean, this is something that you are familiar with. I have to do it every semester. So I use this as an example. So for example, take course grading. It can be done with absolute thresholds. I could just tell at the beginning of the semester, greater than 85 is A, greater than 75 is B, so on and so forth. But if someone gets 84.9, should I give that person A or B? That is the question, right? If you just use purely automated one, it will give a B. Whereas if I do it manually, I can take it into account. I can see there is a very small difference, and that difference I know does not make so much difference. So I can tweak it in order to do that. So this is something that is difficult to do in an automated way. So humans can deal with small variations. It can be, so you can also do it using a curve. I usually do it. Say class average plus one standard deviation is A. Again, if someone missed A grade by a very small amount, or I can take into account, for example, so we look for separations for clustering. You can take exception like effort put in, class participation, types of questions asked, active on dashboards. All those things can be taken into account while doing. So there are some advantages to doing some things manually or doing automated, but you can also combine both of them. You can first do it in the automated way and then look at it carefully to see whether you want to make some changes. So that's what you should be thinking about. What if the class average is 82%? If the class average is 82% and the standard deviation is 8, then in my way of doing it, only people with 90 and above will get an A, right? But I mean, everyone is doing very well. Class average is 82%, means they're all doing well. So I may want to reduce that. I may use average plus 1/4 standard deviation or half standard deviation, just to make sure, we fairly and consistently evaluate what we are doing. So all of this is part of the analysis and what you do with analysis. So should one give 8 to 90 and above only? So data analysis alternatives, advantages of automated approach: fast, can use more data, complex data, can generate reports, can generate plots and visualization, can choose alternatives, easily compare analysis. However, explanation may be difficult. So this is one of the problems we have encountered, and today there is a whole field of research called explainable AI. You might have heard of it. Explainable AI is mainly how do we explain our answers. So when you get your answers from ChatGPT, you don't know how it got their answers. It's a black box. And you just, either you believe it or you don't believe it, but you don't have any explanation as to how the answer was derived. And this is easy in certain models, it is difficult in certain other models. We will see a little bit of that. For example, it's very difficult to explain neural networks. Why you get that for a neural network is extremely difficult to explain. Generalization is also very difficult. So my assertion is, should not blindly assume the output as correct. You need to do sanity check, validation on small sample data. So even if you have large data, take a small sample, preferably a representative sample that you can manually verify. Run it and see what it gives. Make sure it is doing what you expect it to do correctly. And then hopefully you can trust it on the larger data. So data analysis is not as easy as you think. It looks easy because just apply an algorithm and throw the result. I think that it is not what it is. You need to really understand that. So bottom line for data analysis is, we want to process large amounts of data. We do have large amounts of data. We want the flexibility to slice and dice data in many ways. We want to do it very fast. We want to do it incrementally. This is another important issue. In mining and in analysis, you have analyzed data up to 2025. Now you get the data for 2026. You don't want to reanalyze the whole data set, right? That is too expensive and too cumbersome. Is it possible to do it incrementally? That means by adding this data and making sure the results are correct for the whole data, not for just this year data. And that's a real challenge. Doing things incrementally is not very easy. We want an efficient approach. Efficient, I mean, we want good performance, we want good speed up, we want scalability. I just added, we also want no liability if something goes wrong. This is what you hear from all the companies. Airlines, you call them and say, "Sir, this is not our problem, it's a computer problem." Who is designing the algorithms for computer? Themselves, right? So it's always easy to blame it on the computer. But it is not really the computer that is making the mistake. It is the human who wrote the algorithm or would not understand the decision is making the mistake. So we want to compete others, outcompete. This course is tailored for data scientists to understand the subtleties, issues, and other things. So what tool should we use? So I mentioned this, but today widely used tools are, Python is used. I'm not a very fan of Python for various reasons, but Python is very easy to use. very easy to understand, very easy to program. And also there are tons of packages that come with Python that are tailored for data analysis and various kinds of analysis. So it's a quick and dirty way to do things. Whereas if you want to do the same thing in Java or C++, it takes a much longer time and you have to spend more effort in doing that. So that's RStudio is very popular for statistical analysis. Pandas is, I don't know how many of you learn or you are taught. There is others, SPSS, MATLAB. The question many times they ask, which one is better and which one should I use? Now there is no single answer. There is no silver bullet. You really need to understand that. It depends upon who you ask and what the needs are. All are useful for basic analysis. So if you are doing more statistical work, RStudio is better because there are more packages and more things implemented in that SPSS. So there is also a learning curve. Varies from person to person. So that's also important to understand. It's not the same. Learning Python may be faster than learning RStudio. Learning SPSS and MATLAB may be a little more difficult. So there is a learning curve to learn any of these things, but all of them may be useful for different purposes in different ways. So you cannot say just, I will just learn one thing. You should be willing and prepared to look at alternatives. So, brief history of information. This is for Gen Z perhaps who do not know what this is. So information can be of two types. Till 1946, we were mainly dealing with analog data. So analog data is mainly signals. It's not digital. So when you go and take your EKG, for example, you get an analog output, which is a curve that goes up and down. That's a signal-based curve. But we have sort of transitioned into digital form. And for the digital form, these are my classification. You can think of it, data in the digital form, there was a pre-database management system where data was analyzed without using a DBMS, post-DBMS, and post-internet. If you are interested, there is a book called The Information by this guy. Very interesting reading, but it's very huge. 1,000 pages if you have patience to read. So where did we get the notion of a bit? We understand it today. This was put forward by this guy, Claude Shannon. You might have heard of Claude Shannon of Bell Labs. Used the word bit in 1948 as a unit of measurement of information. Today we just say, 5K, 10K, GB, all are bits, right? But there was no notion of bits before he put out the notion of how do we measure information. Okay, there was no way to measure information before, and this came about in a paper. There was no way to measure information before. Introduced the notion of redundancy to correct errors in transformation. So all of you have heard of CRC, cyclic redundancy check. When you send something and when it is received on the other side, how do you know the transmission is correct? In order to test the transmission is correct, you use all this CRC and other codes, and that will tell you whether the transmission is correct. All this came out. Interestingly, in that book, it talks about the notion of error correction was used by drummers in Africa 200 years ago. They have used it for communication from one village to another village. So here is a real question for all of you. We had two transformative events in the last 1,000 years. So two transformative happened in the last 1,000 years that changed our life significantly. And I'm sure all of you are aware of it, but can anyone tell me what was the first event that changed our life in the sense that changed the volume of information, volume of data that we are dealing with, and what was the second information that further intensified the volume of information and the data we are dealing with. Can anyone take a guess? If not, anybody take a shot? 50-50, you're either correct or wrong, so you'll be 50% right.
Introduction of social media. After the introduction of
Huh?
after the introduction of social media.
Okay, sorry, I'm not hearing you clearly. Can you?
After the introduction of social media.
That's too recent. Now, I'll come to that. Yeah, social media, true, but the first one was the printing press. So think of a time where manuscripts were generated, copies, by handwriting. So people were copying books by writing. So, Bible was written 200 times to make 200 copies. So everything was manual till the printing press came about in 1454, and look at this. From 0 to number of copies, this is 1 trillion within a short period of time. Duplication and amount of volume of data increased significantly because of the printing press. This was way before anything else. Before that, copies were made by writing in hand. So just imagine how difficult it would have been. So this is the first event which happened 800 years ago. So what is the second event? Internet. So here again you can look at the volume of data going into zettabytes. 1 zettabyte is 1 teragigabyte, and this is the expectation of the increase in the volume of data. So these two events changed everything in terms of the amount of information you are going to deal with. And that brought new challenges, new things that we had to do. You could not just process information in the same way. So other enablers, inexpensive sensors, they were one of the things that generated 24/7 data, which was not there. Mobile devices. Today we take images and video left and right. We don't care about it. But nobody sees it after you take it. It just stays on your storage. The storage makers are very happy that you keep taking it and buying more storage from them. Advances in storage technologies. However, this is the key. Analysis, information fusion, filtering of data has lagged significantly. So generating data is easy. Analyzing and understanding data is very difficult. That is the main problem. You can generate lots of data, but then what do you do with that? Okay, so what? These events that came about due to technological advances also meant that it is not enough to create volumes of data. What can we do with this amount of information? NASA has warehouses with tapes, computer tapes. You might not have seen a computer tape, but we use computer tapes for storing data because they are very cheap and you can put a lot of data on that. They have warehouses full of computer tapes sitting with satellite data. Scientists can download that data and do whatever analysis they want to do. So a lot of that is being done. So every satellite that goes up generates volumes and volumes of data. It has to be stored somewhere, but storage is one thing, then it has to be analyzed for something. If you have heard of Hadron Collider in Switzerland, this is the one where you smash atomic particles. That generates, I think, a terabyte of data each day. And then it has to be analyzed and processed. So if you remember, not too long ago, they discovered what is known as the God particle. It came in newspapers. I don't know whether you, something called the God particle. That came out from the analysis of the Hadron Collider data. There was some thinking about the God particle, but they had no evidence for that. But this analysis gave rise to the God particle. So you can Google God particle and you will get a lot of information on that. Geological survey, how can it be put to different purposes in different domains? Now the burden of storing, processing, all of them is on the people who do the analysis. This is a major challenge for data center. Ignorance is bliss. Most of you may not have seen a mainframe. How many of you have seen a mainframe computer? Nobody. I'm so surprised. Let alone what a computer looked like before mainframe. A lot of people today grow up with a powerful computer in their pocket. What you have in pocket is more powerful than the supercomputer we had 25 years ago. More powerful than the supercomputer. For them, it is very difficult to imagine a world where one had to go to a computer center, submit a job, wait for a day or two to get the results. Imagine the patients required a single syntax error correction takes one day. I remember the first IBM computer in India came to Indians of Science in 1972 when I was a student there. And they had a computer center, they built a new building, air conditioning and all that, very fancy, and we were using card decks. So you type your program, punch your program on a card deck, go and submit there today, then you go back tomorrow to pick up the printout. If there is one syntax error, it's gone. You have to correct it and give it again, wait for next day. This was the cycle time for running computer programs. Just imagine how it would have been to do anything in that environment. Indeed, we have come a long way in a very short, let us understand. So here are some, I put this mainly for you guys. This is a computer called Minsk series. This is a Russian computer before the mainframe. Imagine the memory it had was 4K, not 4 GB, not 8 GB, 4K. I hope you understand what K is, kilobytes. Not megabytes, not gigabyte. And could program through console, so you could program through the console. It used Nixie tubes and vacuum tubes. I don't think you have even heard of what a vacuum tube is. That's a precursor to diodes and the printed circuits and digital circuits. Here is another early computer using printed circuits. It used to occupy this room, bigger than this room, and it has to be cooled. Here is the famous IBM 360. This was one of the first mainframes produced by IBM, and some of them are still being used today, So and you can take a look at the disk drive. This is the disk drive, commercial disk drive with 5 megabytes capacity. This whole thing is 5 megabytes. Today, what is in your pocket is 256 gigabytes. So think of it, what you have is 10,000 times bigger than that. So this had integrated circuits, 512K memory, multiple disk platters, lots of magnetic tapes, card readers and printers. So today, a 250 GB micro SD card measures 5 by 8 by 3 by 8 and weighs about 2 grams. Costs about, it's less than $24. This was the disk that was being used with the IBM 370. These are the tape drives I was mentioning. They're like huge refrigerators. You mount the tapes. You mount the tapes here. Data is stored on the tapes, and you read it through your program, just like you read a file, and then process it. This is the early disk drive. This is like a washer. Capacity 50 megabytes, about the size of a washing machine. This is a Russian computer equivalent of IBM 360. In IIT Bombay, we got one of these machines. I ended up working on this machine. We could write assembly programs and Fortran programs in those days. So in a span of 70 years, we have come a long way. We have computers in all shapes and sizes. We have server farms with 10,000 plus machines. You can even program your dimmer switch, rollable LEDs, Google Glasses, VR systems, embedded systems, and it's improving each day. So think of, ChatGPT is evolutionary. Think of LLMs. So I think this may be the last slide for this one. So I'm going to show this. So I won't go through all of it because right now we have just entered this part. Whatever I showed you before until now is around 1970. And we have made progress all the way to big data analysis and big data science. And I feel that a little bit of understanding of what has come about is useful to put things in a perspective, put things in a context. Otherwise, there's a tendency to take things for granted. Oops. Okay, so this is the end of the first lecture. So we are going to take a 5-minute break and then come back for the second one.